Hi guys, in this video I will first introduce a few functions from the standard library for string handling, and with that I will motivate why we need for our compiler project another data structure for handling strings. So far we were just reading input character by character, and for the lecture this was sufficient, but sometimes we also would like to read in a complete line. Now how would we implement a function for that? This certainly requires dynamic memory management, because in advance you do not know how many characters such a line will contain. So you could start with some initial buffer, with some initial capacity. Then you read in character by character, append this character by character to the buffer until you either see a new line or reach the limit of this buffer. If you reach the limit of this buffer, you have to reallocate this buffer. Then continue, of course, to read in character by character until you either see a new line or reached again the limit of this buffer. Then you would reallocate again if you have reached the buffer, and so on. That means in general you will have to reallocate several times before you then see this new line character. Then you also should append a 0 byte to this buffer. So this also should fit into the buffer. And then you return a pointer to this buffer. So a pointer to the first byte in this buffer, which then would be a pointer to this found string. And this sounds certainly familiar, and actually we can reuse something that we already have implemented for that. That's of course our string class. The implementation could simply have one instance of this string class, initialize it first, make a clear string, then read in character by character. Each character gets appended to this string variable until we found a new line. And internally, this method for appending characters would do the memory management for us. And then we somehow return a pointer to this string. And that would be it. Now what we actually will do, however, we will not use our own implementation for that. We will use this function getLine from the standard library. Now let me explain how to use this function. Let's begin with the declaration. The return value in general will be the number of characters found. That means 0 would mean we have actually the end of file reached. No more character can be read in. If you have a return value of 5, it means 5 characters were found in this line. And this includes the new line, not the 0 byte. So you would expect that the return value would be a non-negative value and the type therefore unsigned integer. But actually this return type is s size t. And s size t is a signed integer. The size of this is the same as the size of size t. The negative values indicate that some error happened, which is handled here also, because you also can read in something, for example, from a file, and then things can go wrong. The first parameter to this function is a pointer to a character. What you need to have before you call this function is a pointer to some initial buffer. This buffer can be empty, then you simply have a null pointer. But this function always in general has to reallocate whatever buffer you come up with. So that means you actually have to pass this pointer by reference to this function. And because we do not have call by reference in C, we have to pass the address of this pointer to the function. That's why you have here a pointer to a pointer. The second parameter is a pointer to a variable for storing the capacity of this buffer. And the capacity is certainly always non-negative. You don't want to have it doesn't make sense to have a negative capacity. And also this needs to be changed if the reallocation was necessary. So you also have to pass a pointer to that. Here you actually do not have to zero initialize this capacity if you start with an empty buffer, but I think it's a good style to do it anyway. And the third parameter is simply a file pointer. So if you want to read in something from standard in, you pass here standard in as parameter. Now let me show you how to use this without actually looking at the return value. So here no error obviously occurred, and the return value would be now the length of this hello string including the new line. That means now internally some allocation happened, and now line points to this buffer that was allocated, and capacity will now be at least the number of characters in the strings, including the new line and including the 0 byte. If I call it again and the next string fits into this buffer and no reallocation took place, then line will still point to the same buffer and the capacity will not have changed. But in general, each time you call this function, this pointer might be different from before, and also the capacity might have been increased. If you want to read in line by line until the end of file was reached, you have to use this pattern. Recall that this function might return something negative. That's why you should check whether the return value is larger than 0, and you should not use here unequal to 0. Unequal to 0 would work if no error happens. Then unequal to 0 means at least 1 byte was found in this line. But then you would do something wrong if the return value was -1, for example, if it was negative. Now let me show you in the demo how to use this function. I get back with len the number of characters in this line. I pass a pointer to this line buffer. I pass a pointer to this capacity. And in the loop I print out all these things. Now let's begin with some short string, hello. And then you see the capacity is a bit more than just the length of the string. If I have a longer string, then now the capacity was doubled. And what is annoying here is that I also have this new line in the string. And actually I don't want to have this for a later test. The index of the new line is len -1. And I simply overwrite this new line character with the 0 byte. And that means I now have the 0 termination at the place where before I had the new line, and now I have this strings that I actually want to have later. Of course, you also have to release the memory that was allocated for you by getLine. And for that we simply use a free after the while loop. And this will work even if line is the null pointer. For example, if the user typed in Ctrl D, then we would have here still the null pointer. I will later show you the main page for that. But now let's first put everything and rerun all tests. So we first had hello. So of course the same output. And now let's also test what happens if I type in Ctrl D. So no crash at least. Now let's convince ourselves that this is actually what we can expect by looking at the main page for free. And the relevant important sentence for this is, if pointer is a null pointer, no operation is performed. In the header file string.h, several functions are declared that are implemented in the standard library. I want to first show you the function string length for getting the length of a string, and I want to give you an idea how this function could be implemented. On the website I will actually provide you a link to the actual implementation that comes together with GCC. Now if you have a string and a pointer of course to this first character of the string and pass it to this function, the implementation could look like that. That it first makes a copy of this pointer, so you have 2 pointers now to this first character. Then you have a loop which will increment this second pointer until it points to the terminating 0 byte. And then you're done with this loop and compute this distance between these 2 pointers and return this distance. This of course would be the length of the string. So this of course means the longer the strings are, the longer it takes for this function to return. So the performance depends on the string length. In the video on program arguments, I was already using this function string compare for comparing 2 strings. It returns a signed integer. It returns 0 if both strings are equal. It returns some negative value if the first string comes alphabetically before the second string. And it returns something positive if the second string comes before the first string. The implementation of this function could be like that in a loop you increment both pointers until either one of them points to the 0 byte, or these pointers point to different characters. And after the loop, you then just return the difference of these two characters at the end of these two pointers. For copying strings, you can use the string copy function. This function has two parameters. The first parameter is a pointer to the destination string, the string that will be overwritten by this function, with a copy of the source string. And the second parameter is a pointer to this source string. The return value then will be a pointer also to the destination string. The implementation is simply a loop that will copy character by character from the source string into the destination string, including the 0 byte. So what does destination string actually mean? It means that you have some memory location that actually can be overwritten. So that means you have some buffer that therefore should be sufficiently large to actually store a copy of this source string, including this 0 byte, because this is a loop that just copies character by character until it has copied the 0 byte. It will not check whether this destination string is sufficiently large. That means in this example, everything works fine because I have a buffer that is sufficiently large to also include this 0 byte. But if I would have forgotten that I have to count in the 0 byte, if I just would have chosen for this size of the buffer the length of the source string without adding 1, then I would have a problem. Then I would have undefined behavior, because this might give a segmentation fault. It also might override some other variable, or nothing might show up in the test cases because I just override some memory cell that is nowhere used. And undefined behavior is the worst thing that you can imagine. Now, there are other functions that I not explain here, but on the website you will find links to the man pages. This is, for example, string n copy, which will stop copying after it copied n bytes. And here I just want to mention this is also not safe, because that means sometimes you will have in the destination a non-zero terminated string. And okay, it's inconvenient at least that if you print out the string, maybe you also get whatever comes after this string in memory. Another copy variant is string L copy, which makes sure that you have always a zero terminated string in the destination. That means if you are unsure about memory management, then you have to use some of these variants, but we will actually make sure that our implementations will correctly compute the size of the destination buffer, and we will actually use string copy. Comparing two strings for equality is an important operation for a compiler, which is frequently used. For example, if you have an identifier found in the expression, you have to check whether this is a declared variable or not. For that, you have to use a loop, which goes through the elements of the symbol table and checks whether the identifier of a symbol is the same as the identifier found in the expression. And that means you don't want to have a call of a function that involves another loop, a function like string compare from the standard library. You simply want to compare two pointers for equality. And for that, we will implement a simple data structure for a set of strings. And in a set, you only have unique elements. You cannot have two different elements with the same value. That's why I call this elements of the set unique strings. And we will provide a function for adding a string to the set. Now, adding a string that is already in the set is not an error. You simply have afterwards the same set as before. This add function, therefore, should work as follows. If you add a string to this set, which isn't already in the set, you get a pointer to a new created unique string. And otherwise, you get back a pointer to an already existing unique string. So that means afterwards, you simply can compare pointers, like here, or here, or here. And in the demo, I will explain you the complete interface of this new data structure. You should also be able to see whether a new identifier was actually added to the set or not. And of course, we also want to print out all the elements of this set. Let me first rearrange here things so that you also can see the header file. And then I also want to have a terminal for compiling and testing. Okay, so first I want to use this function unique string add for adding every line, and every line will represent an identifier. And after that I want to print out the string for this identifier, and for that I can access this member C string. And you also can access this member len for getting the length of a string without needing to call string length from the standard library. And then in the end I want to print out all strings that we collected in this pool of unique strings. Okay, now let's compile this and test this. I just type in a few identifiers. So X, Y, ABC, and then X again. And then you see this pool just contains 3 strings and not 4. Now let me show you why I need this second variant for unique string add with this underscore in the end. I want to check whether actually a new set element was created or not. And this variant expects this second parameter pointed to a boolean, and after this call edit is true if a new set element was created and otherwise false. And if this element was newly created, then I want to print new identifier. Okay, then let's test this again. New identifier, and this was already in the pool. Now, why are these pointers returned by the add functions const pointers? Because it should not be possible to change a string in this pool. Unique strings should be, of course, constant strings. And if we try to do this, we will get an error from the compiler. And if we would discard this const qualifier, then at least we will get a warning, and of course this warning could be turned into an error message. So let's undo this changes here and compile again so that we see that we are back to a working state. Then let's also simulate that I first want to check whether this identifier isn't a keyword that was reserved. So for that I create a table of reserved identifiers, a table for keywords. I simply use an array and initialize it with some unique strings, if and for and while. And with that I can check how I can do simple string comparisons by comparing pointers. I can now use a loop for iterating over this array elements. The number of elements is the size of keyword divided by the size of the first element of these keywords. And in this loop I now can use a simple if, where I compare the pointer of the keyword with index I with the pointer identifier, and if this is the same, then this identifier actually cannot be used as an identifier because it's a keyword. So let's print an error message, and then I also should set this error flag to true in this case. And then after this for loop I either could exit, or in this case, in this test, I simply will continue to read in the next line. I will ignore this input. Okay, now let's test this again. So that's okay, and this is not okay, so we get this error message. For is also an identifier, cannot be used as an identifier, but form can be used. That's it for this video. Now in the exercise, of course, you should implement this data structure for a set of unique strings. Here you can keep it simple, use a single linked list for representing the elements of this set. Then when you add a string to this set, you iterate over these elements of the set. If you find the string in these elements, then you simply return a pointer to an existing list element, and otherwise you add a new node to the list with the new string as element. And here, of course, you have to use the string compare function from the standard library. So that means for two reasons this is kind of expensive to add a new string. You have a list that gets longer and longer the more elements you have in the set, and you also use this string compare function. At least one thing we can improve later. The data structure for representing this set can be improved by using a hash map instead. Then adding new strings will be faster. Another thing will be improved later. We will, in this current form, never release the memory of this pool of unique string objects until the program terminates. Then the memory gets released by the operating system when the memory of the complete process gets released, which is kind of okay for now, because in general we will need this unique strings until the program terminates. But it's kind of unnice if you use tools for checking your program for memory leaks. A tool like Valgrind will state that some memory leak is actually in our program because we never released this pool of unique string objects. We will deal with this later, that we actually have a way to release memory of pools like for the unique strings, and also we will have other pools of certain objects, and we will deal with all of these problems in one sweep, but not now.